Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Today we're going to have a lot of fun introducing new concepts. We're going to face the elephant in the room, which is how do we actually get at the idea of a sequence? Today we're going to move some steps towards this. We're going to talk about sequences, on sequences, and new kinds of things called clips. So we're going to take a novel approach to very familiar things that are mostly sloughed under the carpet. Okay, the difficulty with the idea of a sequence is that although we all have an informal understanding of it, in practice there's just so many different ways of thinking about what a sequence really means. Let me illustrate that by giving you some of the possible answers to the question, what is a sequence? So, first example. Here is 5, 6, 8, 13, 4, 4. That certainly looks kind of like a sequence. Here's another example, slightly different. We have the numbers n equals 1, 2, 3, 4, 5, and associated to those we have numbers 70, 51, 14, 3, 2. So here's the sequence, but now we have the positions of the sequence clearly marked. This is the first one, this is the second one, third one, and so on. It's not entirely so clear what the indexing is at this stage over here. This first one here could be associated to the number 1, but often we want to start sequences with 0, so this might be the 0th one. Here's another quite different sequence, s sub n equals n squared plus 1, utilizing a function or a rule, in this case a polynomial. The index is, in this case, specified. Okay, that's typically considered a sequence. Here's a quite different kind of sequence. It's a recursive sequence. We're given an initial value t0, another initial value t1, and then some kind of recursive rule that allows us to calculate further ones given previous ones. Here's another kind of thing, Rn. It's a binary sequence consisting of just zeros and ones. 0 if n is composite, 1 otherwise. That's okay. We could generate a sequence like that, but only up to a certain point. Once we get up to the trillions, it starts becoming very challenging to determine whether something is prime or not. And beyond a certain point, we have no idea of how to really determine, to verify that a given huge number is prime. So there's something computationally inaccessible to this sequence, at least once we get beyond a certain point. Here's another kind of infinite sequence, as opposed to this kind of finite ones here, where we just have some numbers separated by commas, and then eventually we have 3 dots. And when we look at it, there's no apparent rhyme or reason to the numbers. They're going all over the place. And so it's not clear at all to us what the 3 dots really mean. This is a huge aspect of this subject, that we're using 3 dots in so many different ways, and the 3 dots, they're just ambiguous. We don't really have a handle on it. So for example, in this situation, the 3 dots could mean a number of quite different things. One of the interpretations or understandings is that the 3 dots mean there's a pattern given, associated to the sequence. There is somewhere else, maybe on the reverse, the pattern, the rule that generates the sequence. But another possibility is that there is a pattern, but it's just not given. In other words, we are guaranteed that there is some pattern somewhere, or a rule or a procedure or something, that is written down somewhere else, but it's not accessible to us. That's quite different from this one. And it's also crucially different from the situation where there's no pattern given. So we don't know whether a pattern exists or not. Maybe there's a pattern, maybe there isn't. And maybe we're even told that no pattern exists. It might be that this thing is generated by some oracle that we're imagining, which is beyond any finite computational process. So it's impossible for us to generate a pattern or a finite rule. But perhaps we're still allowed to think about sequences of that kind. all kinds of subtleties about what exactly the possibilities are for what we're meaning with these three dots. Here's another one, very computationally oriented. We might have a program, a computer program written in some kind of code. A0 equals 0, T equals 1. For I from 1 to 100 do the following, blah, blah, blah. Print A sub T. Then you have these various instructions, and finally the loop closes. So there's some loop that's doing something, and what's actually inside here, well, there might be lots of lines of code, and understanding what that code is, checking it, making sure it doesn't have any bugs, and so on. It's all part of whether we're going to accept that that's actually a valid sequence or not. So these are some of the possible interpretations of the word sequence, possible nuances with the various aspects relating to the specification of sequences, the issue of where it actually starts, and more crucially, the issue of what do these three dots that we like to put at the end of sequences really mean. Another question is, what is the relationship between the idea of a sequence that we're trying to formulate and the idea of a list? In the finite situation, are these essentially the same thing, or is there some crucial difference between a sequence and a list? And an infinite sequence, whatever that is that just a list that is possibly endless? And then there's questions of how to deal with the fact that we generally have finite resources. We have finite amounts of time, memory, power, patience at our disposal. So how are we going to really get at what we'd like to think of as infinite sequences? So most calculus courses, it's safe to say, tries to finesse or basically ignore such questions and just assume that we have a working understanding of what a sequence is. But it's one of the aspects of modern calculus that really weakens it, because ultimately we don't know what exactly we're talking about. So our aim here is to give precise definitions, if necessary, by, first of all, fragmenting the concept. So maybe we don't just have one kind of sequence, maybe we have different kinds of sequences that we should identify. And also by restricting the concept. Maybe we can't get an all-embracing notion that covers all these possibilities. Maybe we have to start smaller. Say, this is just what we're looking at now. Maybe tomorrow we'll expand it a little bit, then next week expand it further. Okay? So more modest aims, but ultimately we're being more ambitious in that we're aspiring to really understand what this notion really is precisely. That's going to be crucial for the integrity of the calculus. So I'd like to start by identifying a simpler building block that we can build the idea of sequence on. And that's the idea of a chain of natural numbers, or more generally a chain of integers. We're talking about consecutive integers, one greater than the previous one. So for k equals 1, 2, 3, and so on, and n an integer, let's say that the k chain on n is this expression here. We start with n, then there's a comma, and then n plus 1, and then n plus 2, and we put all together k successive elements. So the last one will be n plus k minus 1. So altogether there's k objects in this sequential list. So for example, the 3 chain on 17 is 17, 18, 19. The 1 chain on minus 51 is just minus 51. The 8 chain on minus 2 is minus 2, minus 1, 0, 1, 2, 3, 4, 5. 8 of them all together. We'll introduce some different kind of notation to express the same concept. So the chain from 5 to 11, which is a 7 chain, the 7 chain on 5, we might write it like this, C511, where we specify the first in the chain and the last in the chain. A little bit like an interval, but it's an interval of integers rather than an interval of more general numbers. So if we call this chain C, then we could describe it as saying it's the 7 chain on 5. Or we might also want to express it not in terms of its first entry, but in terms of its last entry. There might be situations where that's more important to us, in which case we could refer to it as the 7 chain to 11, describing it or indexing it by its last element. Or maybe we could say the chain 5 to 11. So the chain has a beginning, which is 5, and an end, which is 11, and we could introduce B of C and E of C to denote those. So just some sort of basic concepts having to do this relatively simple idea of just a bunch of successive integers, one after the other, always increasing by 1, forming a chain. Okay, so now let's start with sequences. Simplest kind of sequences, which are integral K sequences. K is, as before, a natural number 1, 2, 3, 4, and so on. So we'll define an integral K sequence. What's that? It's an explicit assignment of integers to the elements of a K chain. For example, here is a 6 sequence called S on the chain from -1 to 4. Here's the chain from -1 to 4. -1, 0, 1, 2, 3, 4. And I'm going to put the chain on the bottom. And on top are going to be the values of the K sequence. In this case, K is 6. S of n. 1, 2, -1, 3, 0, 2. So to each of the integers in this 6 chain, we assign an integer. Now, we can write it like this. This is very explicit. We see exactly what's going on, but it's a lot of writing. So more succinctly, we could write it like this. We could say the same sequence S is described by listing the elements of the sequence. 1, 2, -1, 3, 0, 2, separated by commas. But in addition, we want to know not just what the elements are and their order, but also which integers they're associated to. So a sequence is an assignment of integers to the elements of a chain, and we want to be able to see the chain. In particular, we want to know what the indexing is that each one of these elements has. So you see that I'm putting a subscript here, -1, 0, 1, 2, 3, 4. It's kind of going back to an older tradition that's actually centuries old, that when you had a sequence of various things, often there would be some exponent or index that would tell you where you are in the sequence at any given point. So you just look at this one here. You don't have to count from the beginning or the end. You can see, this one is associated to the number 2, the index 2. Now, admittedly, this is, more work. Usually we just like to write down the sequence. So we could do that more efficiently in a number of ways. One obvious way is to write it like this. Write the sequence S and make the dependence on the chain incorporated here in terms of bounds. Put a -1 as a subscript and a 4 as a superscript. That's telling us that this is a sequence on the chain -1 to 4. So this is associated to -1 to 0 to 1 to 2 to 3 to 4. And another possibility would be to write something like this, but be a little bit lazy, and just to write that first one, the first index -1. So we know sort of where the sequence starts. Technically then, we should be able to figure out what all the other ones are. Even though it's then making it a little bit more onerous for us to extract information easily. There's something complete and attractive from a computer science point of view, having a sequence like this, or in this form here, we can see exactly where everything is. And also the limits of the chain and the size 6 are clear. Given a big sequence, one maybe having millions or billions or trillions of terms, it's nice if we know in advance, if we can see how big this sequence is without having to actually troll through it and count all the elements. It's nice if there's some data somewhere that we can read off, like in something like this. We can say, this is a sequence from 0 to 10 billion. Okay, and there it is. But we already have a prior sense of its magnitude and its extent. That's very useful. And let's also introduce a default starting position to be 0. So if we have a sequence written like this, s equals 5, minus 1, minus 1, 2, and there's no index floating around anywhere, we're going to assume that this is the 0th one. This is a chain that begins at 0. So this is the 0th one, the first one, the second one, and the third one. So this means s equals 5 sub 0, minus 1 sub 1, minus 1 sub 2, and 2 sub 3. Just a convention. Okay, so now we have some sequences at our disposal. We have defined the idea of a k sequence for some k equals 1, 2, 3. But in particular, all the sequences that we have so far introduced are all what we ordinarily call finite sequences. In particular, none of the, or at least most of the entries of the online encyclopedia of integer sequences, Sloan's remarkable compendium, are not really yet in our picture because most of those sequences are things that carry on. So we do want to extend our understanding, but that might be a little bit down the road. And now we come to what I think is a very novel idea, and I think a very useful one. The idea of a clip. So we're going to talk about clips. So in filmmaking, you take a clip, means you have a long sequence. A clip is some shorter part of it, like a small segment, video segment, or maybe an audio segment, and you can manipulate clips and combine them in various ways to make longer videos. So this is the basic idea, that a clip is a portion of some longer entity that's somehow just cut and taken out of some longer thing perhaps. Okay, we're going to say that a clip in our context is a representation of a portion of a sequence. When I say portion, I mean a sort of consecutive portion where we're taking things which are adjacent. So let me illustrate that. So here's a sequence, s equals 1, 2, minus 1, 3, 0, 2. It's a sequence on the chain from minus 1 to 4. That's a sequence which has 6 elements. Here are some clips from it. Okay, so the first clip is L. Let's have a look at L. L is 1 sub minus 1, 2 sub 0, minus 1 sub 1, 3 sub 2. Exactly the same as the first 4 elements of our sequence, followed by 3 dots. So what L is what we might call a left clip of the sequence S. We've taken the leftmost portion of the sequence and gone a certain way into the sequence and then lost information, then truncated, then removed the rest, or just ignored the rest, or maybe it's not available to us. And these 3 dots represent the additional information that the sequence contains, but that we are not in possession of. You can think of it as a loss of information. The clip just does not extend beyond this point. But the 3 dots are telling us that there is at least something after this one. This is not the end of the sequence. These 3 dots guarantees that there is actually something further on. We'll call this a left clip because it starts at the beginning or the left point of the original sequence. Correspondingly, here's a right clip. Its name is J from the same sequence. It has 3 dots and then 3 sub 2, 0 sub 3, 2 sub 4. So it's the sequence 302, which is the last portion of the given sequence, and 3 dots in front of that telling us that there's more to the sequence than just this. This is a snapshot of the rightmost point, or a rightmost part of the sequence. And we can combine both ideas. Talk about a double clip. Here's where we just extract something from the middle. Cut, extract, and ignore stuff on either side. So K is also a clip from S. there's 3 dots, and then -1, and then 3, and then 3 dots. But the -1 and the 3 come with positions. We know where they're from with respect to the original sequence. And then there's a fourth thing sort of to complement these other 3, which is a total clip, where you're not excluding anything, just the original sequence. We'll call that also a clip from the sequence. That's the total clip. It's all of it. And let's agree that a clip must have at least one element, so putting 3 dots is not allowed. Now, you're actually familiar with this concept a lot, but in the context of functions. So if we have a function like y equals x squared, we draw our usual axes and we draw a picture of y equals x squared. It's not really a picture of y equals x squared, is it? Because our x-axes are bounded by some convenient bounds. The y-axis, we're only showing a part of that. Right? The whole picture is really only a small part of this much bigger entity that actually goes on in this direction and up. Right? We're just actually recording a small portion of it. And in some sense, it's rather an arbitrary portion. Why go from -5 to 5? Why not look at it from 1005 to 1017? Of course, it'd be perhaps less interesting. It'd be way up there somewhere, but it's still a legitimate kind of view. So we do this actually a lot without making it explicit. We take things which we are imagining extend in other directions, and we're taking a snapshot of them and presenting the snapshot as the real thing. So we're doing the same thing here, but we're just being more honest. We're really acknowledging the fact that we're only taking a portion of the object. So it's a clip. There's the sequence. These are clips from the sequence. They're partial information. We're losing something. And just as with sequences, let's establish a default condition. We'll say that default is a left clip starting at 0. So if we want to be lazy, we can leave off the indexes, in which case we're assuming we start with 0, just as we did for sequences. So a given sequence will have many clips. These are partial representations of the sequence. We're getting a snapshot of part of the sequence. So here's another example. Here's a sequence S, which is 10, 9, 8, 7, 6, 5, 4. We can see that there's 7 elements, so this is a 7 sequence. And there's no indices at all, so the default is that it's starting at 0. This is the 0th one, the first one, second one, and so on. Okay, so this sequence has a number of clips. And we're going to introduce this terminology to express the idea that a given sequence is represented by a clip. Okay, so S is represented by this clip, 10, 9, 8, 3 dots. This is okay. This is the default. The default is if there's no indexes, or indices we should say, then it's automatically assumed to be 0, and then 1, and then 2, and so on. And that actually is the left, or a left clip from this original sequence. So that's a legitimate statement, giving us a partial leftmost view of the sequence. It's telling us how the sequence starts. But the 3 dots does not mean and so on. Okay? It means rather, and there's more. Sequence is 10, 9, 8, and there's more. It's not asserting that there's a pattern that's been established that we're continuing. Okay? It just means that there is more to the sequence. How about this? A double clip, 3 dots, and then a 7, and then 6, and then 3 dots. That might look like a legitimate clip, obviously identifying that portion of it. But we are not going to allow that as a legitimate clip. At least not the way we're defining clips currently. The reason is because the position of the 7 and 6 here are indeterminate. We don't know where they are in the original sequence. However, this modification, where the 7 has underneath it the index 3 and the 6 has the index 4, that is okay. All right, that's 0, 1, 2, 3. That's the third one, that's the fourth one under the natural indexing. And so this is an honest representation of these two elements. It's telling us where they actually are in the original sequence. With sequences, we want to know where things are. What about this? 3 dots and then a single 4 with a 6 as an index. 0, 1, 2, 3, 4, 5, 6. That's the correct index. This is a legitimate clip. It's a right clip. It's got to have at least one thing in it, but it does. This thing, however, is not defined. 3 dots, that's no information. We're not going to consider that a valid clip. So notice this notation here, the equal sign followed by a greater than sign, making an arrow altogether. This is not really the logical implication that I usually write in red. This is a different mathematical symbol that is a lot like equals, but it's not quite equals. S does not equal this, but S gives rise to this, or S can be represented by this clip. The clip is less than the sequence. The sequence is the whole thing. This is just a portion of it, a view, a partial capturing of some of the information for it. Okay, that's why the arrow goes in this direction. We cannot recover the sequence, generally speaking, from the clip. We've lost information. So far, all the sequences we've been considering are finite sequences, and they're all expressed by explicitly stating all of the elements. What about when we want to have some kind of rule or formula? What are we going to do then? So we're going to introduce now another kind of sequence, a polynumber sequence, which is something that comes from a polynumber or a polynomial. So I remind you that we like to think of polynomials in this polynumber notation. So here is a polynumber. It's a vertical list of numbers with a little bracket on top, sort of alerting us that's a polynumber. And this one, 2 minus 1, 3, has an alternate representation in terms of powers of alpha. 2 minus alpha plus 3 alpha squared. That's a polynumber, which you can think of as being essentially just a polynomial expressed in a particular way. Now, given such a polynumber, we may associate to it a sequence. Well, actually, quite a lot of sequences. And we're going to introduce this notation. P of n, P is the polynumber, P of n enclosed in some brackets, but it's a little bit funny because there's a square bracket on the left-hand side and a kind of a pointy bracket on the right-hand side, suggesting this is something going in that direction, which is roughly our intention. And there's also indices, 1 to 4. What is this? Well, this is a sequence. P of 1, P of 2, P of 3, P of 4. So it's obviously a sequence built on the chain from 1 to 4. And the values are just obtained by applying the polynomial to the elements of the chain. P of 1 is 4, and P of 2 you can check is 12, P of 3 is 26, and P of 4 is 46. So this is a compact way of representing this sequence. And it's a rather specialized kind of thing because we're only allowing it at this stage for polynomials or polynumbers. And we'll write this thing here. We'll allow ourselves to, instead of writing P of n, we'll allow ourselves to actually write the polynomial or polynumber with an n in it. So 2 minus n plus 3n squared. N for us, little n, will be a letter that's intimately connected with natural numbers typically and the elements of a sequence. So we'll want to make this association that n, we're going to use it often in conjunction with the sequence. So when we see something like this, it's an expression in n, it's a polynomial expression in n, it's got a square bracket on this side, a pointed bracket on the right-hand side, and it's got bounds from 1 to 4, then we know we're talking about a polynumber or a polynomial sequence. So that's a way of getting at certain very regular types of sequences. So with that polynumber sequence notation, we can capture very long sequences very succinctly. We just write down the P of n polynomial in the appropriate brackets and put the indices that we want our sequence to go for. And that expression captures a potentially huge sequence. So it's a very efficient kind of thing. And it's also the starting ground for our first step into or towards the so-called infinite or endless. So besides finite sequences, we do want to consider sequences that keep on going, okay? And because there's so many of them, and they're very interesting. So what we're going to do, though, is approach this challenge in a limited way. We're only going to extend, for now, the idea of a polynomial sequence or a polynumber sequence to the idea of a polynumber or polynomial on sequence. The on for the idea of something that keeps on going. And here is what we're going to be talking about. So here is something that looks very familiar to what we were just talking about. It's a polynomial in here, or a polynumber, 2 minus n plus 3n squared. Polynumber evaluated at n. It's an expression in n, a polynomial expression in it. There's a square bracket on the left, there's a pointed bracket on the right, and then there's indices. There's a subindex here, which is, in this case, 1, and there's a superscript, which is an index. And what is that? That's a plus sign. A plus sign. That is what we'll call a polynumber on sequence. So that is the polynumber on sequence. If instead of having a plus sign there, we had a 5, then this would be a polynumber sequence. Exactly, this would be a polynumber sequence. And it could also be represented in the usual way in terms of writing out the sequential elements separated by commas. In this case, this is the polynumber on sequence, and we are only partially able to express what the corresponding sort of picture of it is, the actual list of elements. Because we're thinking of this as going on forever. Okay, it starts when n is equal to 1 and then n equals 2. So you can start listing them, but there's no way you can keep on going and just keep on listing them, because eventually you run out of resources. The universe is only so finite and so on. But nevertheless, this is actually the object that we're going to call the on sequence. But even though we cannot express it completely, what we can do is we can demonstrate a clip of it. Okay, so here is the polynumber on sequence, and here is a clip for this polynumber on sequence. It's the same one we've already seen before. It's the clip 4, 12, 26, 46, ... And there's more. Doesn't mean and so on, because there's no pattern here that's evident from just these 4 numbers. There's no pattern. We're just saying that this on sequence has these as the first 4, and then there's more. You can generate more, if you want, just by starting to plug values into this thing. You can generate as many as you like, but you will never be able to generate all of them. So this is showing a clip of the on sequence. So we are not going to use the idea of just having equality. We're not going to say that this equals this sequence. We're going to think of this sequence. We see the 3 dots there. We say, aha, we've lost information. It's not the whole story. So that can't be the whole thing. That is just a picture of the real object. This is the real object. This is a picture of the real object. It's a clip from the on sequence. Okay, lots of important ideas today, thoughts to think about, new notation, new ideas, new concepts to get your head around. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.